All right, our idea with total mechanical energy is that it's all forms of energy added together. When we talk about forms of energy, if it's mechanical energy, it's kinetic energy plus potential energy. So total mechanical energy is the kinetic energy plus the potential energy. That's what we're looking to do every single time. So number one, it's going to step us through it. Calculate the kinetic energy of the go-kart. Kinetic energy is 1/2 mv squared. So that's 1/2 times 20 kilograms times the velocity, 10 meters per second, whole thing squared. So that kinetic energy comes out to be 1,000 joules. Calculate the potential energy of the go-kart. Potential energy is mgh. What it's telling me here is that it's at the top of a 30-meter tall hill. So that's going to be 20 kilograms times g, 10 meters per second squared, times the height of my hill, 30 meters. So my potential energy comes out to be 6,000 joules. And my total mechanical energy is kinetic plus potential energy, comes out to be 1,000 joules, the kinetic energy, plus the potential energy of 6,000 joules. 7,000 joules. That is the total mechanical energy. It's the combination of all the potential energy plus the kinetic energy. How much work must be done to stop it while it's still at the top of the hill? Well, if it's stopped at the top of the hill, stopping means the kinetic energy is gone, but the potential energy is still there. So I lost all my kinetic energy. So my change in kinetic energy is negative 1,000 joules. My change in potential energy is 0. So the work done is just the change in kinetic energy, negative 1,000 joules. That energy, if we're stopping something, usually goes to heat. Think about your brakes heating up in your car. What force must be exerted to stop the cart in 5 meters? Well, work is equal to negative 1,000 joules. Work is also equal to force times distance. So force times distance is equal to 1,000 joules. If that distance is 5 meters, divide both sides by 5, and that force comes out to be 200 newtons. We would have 200 newtons required to stop our object. In order for the go-kart to have 6,250 joules of kinetic energy, how fast does it have to go? Well, I know kinetic energy is 1/2 mv squared. So if we plug in what we have, 6,250 joules is equal to 1/2 times the mass of 20 kilograms times the velocity squared. So in order to solve for the velocity squared, we got to multiply both sides by 2. It gets rid of the 1/2. We got to divide both sides by 20. And that tells me that velocity squared is equal to 1,875. And so in order to get the velocity, we have to square root both sides. And so that velocity comes out to be 43.3 meters per second. Question 2, a block is sliding with this speed, 3 meters per second, on a frictionless table 5 meters high. Calculate the kinetic energy of the box. Kinetic energy is 1/2 mv squared. So it's 1/2 times 4 kilograms times 3 meters per second, whole thing squared. So the kinetic energy comes out to be 18 joules. Calculate the potential energy of the block. Potential energy is mgh, so it's 4 kilograms times 10 meters per second squared times the height, 0.5 meters. So that comes out to be 20 joules. And so the total energy is the kinetic energy plus the potential energy, or 38 joules. We just add those two together. If all the block's potential energy were kinetic, how fast would it be going? Well, in that case, the kinetic energy, which we know is 1/2 mv squared, would be equal to 38 joules, and it'd equal 1/2 times the mass, 4 kilograms, times whatever the velocity is squared. So we would multiply both sides by 2, divide both sides by 4, and that tells me that 2 times 38 divided by 4 is equal to the velocity squared. So to get the velocity, I'm going to square root both sides, and that tells me that the velocity, if all of the energy were kinetic energy, would be 4.36 meters per second. That would be the velocity. If all the block's energy were potential energy, how high would the table have to be? Potential energy I know is mgh, so if all of the energy, all 38 joules were potential, 4 times 10 times the height, we divide both sides by 40, and that height would have to be 0.95 meters. A model airplane has a mass of 50 kilograms. It has 10,000 joules of kinetic energy and 15,000 joules of gravitational potential energy. Calculate the velocity of the plane. Velocity has to do with kinetic energy. So kinetic energy is 1/2 mv squared. So 10,000 joules of kinetic energy is equal to 1/2 times the mass of 50 kilograms times the velocity squared. I'm solving for velocity. We're going to multiply both sides by 2, gets rid of the 1/2. We're going to divide both sides by 50, gets rid of the 50, and then we're going to square root both sides because it gets rid of the square. When we do that, our velocity comes out to be 20 meters per second. That's our velocity. If I want the height of the airplane, height has to do with potential energy. Potential energy is mgh. So 15,000 joules is equal to the mass, 50, times 10 times the height. We'll divide both sides by 50. That's 50 times 10. When we do that, we see that the height comes out to be 300 meters. Calculate the total mechanical energy of the airplane. Total mechanical energy is potential plus kinetic. That's 10,000 kinetic energy plus the potential energy, 15,000. That gives us 25,000 joules. How much work must be done to speed it up to a velocity of 25 meters per second and raise it to 40 meters? Okay, there's a lot going on here. My work is going to be the change in the kinetic energy plus the change in the potential energy. Let's do those one at a time. Change in kinetic energy is 1/2 the mass, 50, times the final velocity, 25 meters per second squared, plus 1/2 the mass, 50, times the initial velocity of what we found, 20 meters per second. So the change in kinetic energy, I apologize, we've got to subtract here. So the change in kinetic energy is the difference between my initial kinetic energy and my final kinetic energy and my initial kinetic energy. That change in kinetic energy comes out to be 250 joules. So we gain 250 joules of kinetic energy. The change in potential energy is mg delta H so in this case it's going to be 50 times 10, but delta H here goes from 300 meters to 40 meters. Delta H is negative 260 meters. So my change in potential energy, I'm sorry, I made a mistake earlier. We should have divided by 500 up here, and that makes the height 30 meters. So my change in height here is 10 meters. And so my change in potential energy is 5,000 joules. Sorry for that. And so the work done is going to be these two things added together. So 5,250 joules would be the work required to make those changes happen. Sorry for the mistake there. An object has a mass of 2 kilograms and an initial velocity of 4 meters per second. An 8 Newton force is exerted on the object for 6 meters. No other forces act. So how much work does the force do on the object? Well, work I know is force times distance. So I know the force, 8 newtons. I know the distance over which the force worked, 6 meters. So the work done by that force is 48 joules. That's the work done on the object. What's the final kinetic energy after the force acts on it? All right, so the final kinetic energy is going to be the initial kinetic energy plus our work done. Our work went into that kinetic energy. So our initial kinetic energy is 1/2 times 2 times 4 squared plus the work done, 48 joules. So it's 16 plus 48. My final kinetic energy comes out to be 64 joules. And if I want the velocity of the object at the end, that's K final is equal to 1/2 mv final squared. We're going to multiply both sides of this thing by 2, so the half goes away. We're going to divide both sides by the mass, so the mass goes away. So I have 2 times my final kinetic energy of 64 divided by the mass, which is 2, is equal to final velocity squared. So the final velocity is the square root of 64, or 8 meters per second. If the object is on top of a 2-meter table, what is the total mechanical energy now? So the total mechanical energy is the kinetic energy plus the potential energy. I know that the kinetic energy is the 64 joules that we talked about, plus the potential energy, well, that's the mass, 2, times gravity, 10, times the h, 2 meters. So 64 joules plus 40 joules, we get 104 joules of energy total at the top of the table. How much work must be done to stop the object? Work to stop is just the change in the kinetic energy. So the work done to stop is the change in kinetic energy. There's no change in height, so there's no change in potential energy. So it's 1/2 the mass, 2, times the final velocity, 0, squared, minus 1/2 the mass, times the initial velocity. Well, we don't even have to do that much, do we? When we've stopped, change in kinetic energy is K final minus K initial. So the change in kinetic energy is 0 minus the initial kinetic energy. It's just the kinetic energy on top of the table, 64 joules. So the change in kinetic energy is negative 64 joules, which is equal to the work. We got to do negative 64 joules worth of work to stop the object.